Hey everybody, just want to show a little do-it-yourself job I'm doing. Changing a J1772 charger to have the J3400 or Tesla connector, whatever they call it, a couple different names, but kind of going to be the standard. Kind of a disclaimer for this is definitely you're tickling the dragon's tail by playing around with high current, higher voltage electricity, especially on something you're probably going to charge unattended. So there's a lot of room for error. If you don't know what you're doing, probably this is not the video of a do-it-yourself job on how to do this. I want to show you what I'm going to do. So let's get right to it. So first of all, I got a standard J1772 charger from Emporia here. It could be pretty much any of the brands that do have a cover that you could service and get access to the control pilot wire, the ground, and the two power wires that go to this connector. So lots of reviews on all the different chargers out there. Probably the better way to go is always just buy one from Tesla, or there's other manufacturers, ChargePoint, that have the certified correct one on here. But I was able to salvage this out of a Tesla wall connector that had some type of failure. I will say that Tesla wall connector, I've had them apart a couple times. They're built really, really nice with a lot of safety features in mind, like IR sensor on the temperature of the wires. They have a PTC thermistor in here, I think, that they monitor at the connector. Obviously the connections are also designed for DC fast charging, so they're just way more robust than the small pins on this. And I know firsthand, I have a public charger at work and somebody broke the handle on this. They're just not as durable as this nice sleek Tesla. The company that makes this is Volex. If you go on their website, ironically, you can get the pinout for the AC charge connector. So, the pinout, the specifications, it almost just matches to a J1772. The main exception is the proximity pilot is not the same resistance right here. So they use a UHF controller that needs 12 volts. So whenever you push this little button, it opens the flap on a Tesla car. Opens the charge port. It's a UHF radio signal. You can find lots of other videos on how to hack that. Typically with a Tesla, if you're charging it with something like this Emporia unit, you'd use something like this up to 48 amps. This is included with the car. It's a little clumsy to use because typically you have to unlock the car to release this connector, because Tesla locks the connection from the car side, while something like a CCS or J1772 relies on this. And you can hear a little micro switch inside of this. And that essentially, whenever you push this, the resistance goes lower, I think. And when it's dropped, it's about 500 ohms on that. I think it's the proximity pilot. The control pilot is just directly to the charger. So there's a pulse that comes from this unit that kind of just is pretty much a handshake of how many amps this can deliver, and if it's okay, deliver power. You can find lots of other videos on how that signaling works. They have the European colors for the leads, very different than this charger that uses these very large terminal blocks. You don't want to just jam the wires in there. So I'm gonna actually strip those and put wire ferrules that are the correct size and use a hydraulic crimper to crimp these in place of this. And then you have the I think there's 4 pins right there. 2 of them we're not gonna use and tape off, but we need to have a 12 volt signal or 12 volt power that's isolated for the UHF charge port opener if you want this to work correctly. So kind of see the DigiKey part number for a little AC-DC converter. I checked the isolation, it's pretty good on this unit. There's a lot of different ones out there. You don't want to get some AliExpress thing. This is from DigiKey. But it's suitable for operating at 240 volts AC that I'll tap from this. So we'll see how this all goes. Wired in there, you can find these sometimes used. I think eventually Volex is going to make many of them for the aftermarket charging. The advantage to this Tesla connector, the wire is just so much nicer. I have nothing but good things to say about this Emporia, other than it's built kind of to a price point. Everything's a little more plasticky, and this cord is just horrendously thick. One thing to keep in mind, the mobile connector Tesla, it has the same wires, the pinouts, but it's only intended for 32 amps. So this diameter is a little bit smaller. The wall connector charger that you hardwire into the house, it's got this thicker cord, but still much thinner than what's on this Emporia one. And just keep that in mind. You probably want to configure your charger for 32 amps if you're hacking a cord off a mobile connector. Those are obviously much cheaper. They're pretty inexpensive even from Tesla. There's other adapters. I do not recommend something like this. The problem is the proximity pilot. You hear the micro switch. It actually relies on that. It doesn't really connect to this pin. So there is a possibility of pulling the Tesla connector out of this. They use this on a J1772 car and make an arc at those when it's pulling away. I think those pins are far enough away, so if there is power going through it, you will lose the control pilot, and that will cut the relays on the charger before you break the high current AC connection. But obviously this thing's not certified. This thing's very, very simple, just a straight pass-through J1772 to the Tesla connector, but you don't have the advantage of having that nice UHF door closer. So enough talking about this. I'll give you a little short clips of what I've done to put this onto that. All right, so the first thing I did is you have the line input, the 240 volts from these pair. You got these bus bars going through current sense that goes through the relays and all the control circuit. But also this board is powered. I'm sure I could probably find 12 volts on there, but I'd rather use a separate power supply. And you just don't want to go across line with a little power supply like this. You need some sort of protection, whether it's a fuse and the MOV. So you have the 240 coming in here, going through a couple of protection MOVs to ground and across the two lines. And there's also a spark gap. There's a small fuse here, and there's also a PTC thermistor. And so it's pretty much from this point to here, and same with after that fuse. So on the other side, you can see they have a conformal coating on this board. So I probably should, I pretty much soldered to those 2 points, scraped a little bit of the conformal coating away. I should use some type of silicone sealant or Stelastic, just kind of like how they have on all the components, the white stuff that kind of seal those. Put an extra double insulation on the pair of wires here. So I'm getting 240 volts, but it's protected by some of the protection circuit that's already on here. This thing draws very little current. It's only a 3-watt power supply. You don't need hardly anything. And I'm gonna cover it all with this Captain tape here. All right, so we got the Tesla cord through the cable gland. It's a little bit smaller, so I had to add some extra sheathing on there. The ground wire is a little longer, so if there's any chance of that pulling out, it does have this clamp here. That's the last one that will break away. Along with the ground connection, we have our AC DC converter that's making the 12 volts DC. You have the negative of the 12 volts also tying to ground. This is an isolated power supply. You got line 2 and line 1, so the 240 volts. I got the ferrules on there, the crimp with a hydraulic crimper, and you definitely, it's pretty important to torque these to the specification of the associated terminal blocks that you're using. Personally, like the Tesla solution of using a lug is probably a better solution, but this Emporia one, this is what it uses these. Obviously, if you're gonna test all this, I'd probably leave the cover off. I had set it at 48 amps. Of course, being hardwired and having to correct input from the mains and monitor the temperature of all this. Again, double check the torque of all these connections. They're very critical. The control pilot, so these are the 4 wires that go along with the Tesla connector. The purple is the control pilot. The proximity one is not used, so they just have that taped off. It's probably used in maybe the Tesla charger, wall connector, whatever they call it. The white, I'm not using that. That's the NTC thermistor that's in the connector itself. It probably wouldn't be a bad idea to engineer some solution, maybe a small Arduino or something that monitors this line, maybe even monitors the temperature of these, and breaks the control pilot if there's ever a fault of an over temperature condition. That's probably a future thing I may implement into this. Put some temperature sensors above this, so if there's ever a high ambient temperature, will cut the control pilot permanently, hopefully not a resettable style, so I know there's an issue. Because I don't think there's any type of thermistor on this Emporia unit. The 12 volts plus goes to the blue wire on the Tesla connector, so it's coming from that power supply. So I'm gonna go ahead and button this up, reinstall on the wall, and we'll test it on the Tesla. I have it installed temporarily. I torqued everything. I have a infrared temperature gun, and I'm gonna charge at 48 amps and monitor the temperature of all my junctions. See how it works, just like a regular Tesla. I think you push the button, push it in, and it should start charging. So we'll try it with a death adapter on something that has a J1772. And it looks like it's gonna initiate charging. Yeah, I heard the relays and the contactors click in, and it's charging. I think this charges at 32 amps if I recall. So there you go. A Tesla connector on an older J1772 charging equipment there. So that's how to do it.